You go ahead and start recording now.
Yeah.
Okay. You're gonna do VSEPR and molecular geometry tonight, 1 through 15.
11 is gone.
1 through 15, Jack, the next to the bottom one, VSEPR and molecular geometry.
We only do these middle 15.
Yes.
Oh, okay. Can I write on this?
Yep. No, it's not enough room. You gotta
Not,
write.
I know.
Oh yeah, you're allowed to write on that sheet. That's yours, but the answers are gonna be on a separate sheet of paper. Okay. So we're gonna do the first one together. Get you started, then we're gonna do number 2. You know, all answers are on your sheet of paper, so go ahead and get out a separate sheet of paper. We'll start.
Just those 15.
Yeah, the next to the bottom 15.
I'm just.
Okay, so let's get started. Okay, let's take out your first paper, which is called Guidelines for Drawing Lewis Structures. And we are going to begin.
Yay.
Okay, so first step. Now these aren't the 5 steps that are used for the homework. These are just guidelines to go by. Actually, number 1 up here actually does match number 1 of your answer. When you do these problems, you're gonna have 5 separate answers. So, first step happens to be the first step, like on the sheet of paper. So it says, add up the total number of valence electrons for all elements. These must be all used, okay? If the ions are involved, remember ions, positive or negative, be sure to add electrons for anions and reduce the number of valence for cations. Okay, so let's get started with problem number 1 on your homework tonight, which is NH3. Okay, so we're going to follow guideline number 1, which says, add up, first of all, you're going to separate your compound into individual elements. Okay, now we're going to determine the valence numbers of electrons. What family is nitrogen in?
15.
So how many valence?
5.
5. How many atoms of nitrogen do you see here?
1.
Right, if you do not see a number, it's understood 1. So that's 5 times 1 equals 5. All right, what family is hydrogen in?
1.
Okay, so we're going to write 1 for our valence. How many hydrogens do you see, however?
3.
There are 3 of them. 1 times 3 is 3. All right, so we're going to add up all of our valence, and we're going to get 8 valence electrons. Okay, so that's step number 1 I want to see for the homework tonight.
Okay, this looks pretty easy.
Okay, step number 2, follow along in our sheet. We're going to determine what step number 2 is your drawing. By the way, if you're keeping up, what to do next. So, step number 2, determine which of your atoms will be the central element. Okay, you have a key note here, pay attention. It says, hydrogen can never be the central atom. How do you determine what the central atom is? It's always the one that's the least electronegative. Remember, we've already been over electronegativity trends. The one that's always the least electronegative, which would always be the one furthest to the left. So we don't have a choice here. What is our central element? Nitrogen. It can never be hydrogen.
So, like, if it was lithium, it would work as a central atom?
No, because we're dealing with non-polar, polar. It's all going to be covalent. These are never ionic. When we're doing drawing Lewis structures, these are all covalent molecules. All right, so pay attention to how I'm going to draw this, because this is called the VSEPR theory, the way I draw it. So I'm going to put nitrogen in the middle, because we've already established that's our central element. Now, the way I'm going to draw this is I'm going to draw my hydrogens as far apart from the other elements as I can. And why am I doing that? That is because of something that's called the VSEPR theory. So let's talk about that. VSEPR. So when I draw these bonds, what I'm doing, step number 2 is the drawing. You draw bonds to connect your elements to within your formula. Since our formula is NH3, that means I have 3 hydrogens attached to my nitrogen. So why did I draw it so far apart? Because of VSEPR. VSEPR stands for valence, shell, electron, pair, repulsion. So let's talk about what I mean by that. Pair, repulsion. So when we're drawing bonds and connecting elements to elements, each one of these bonds represents 2 dots. Okay, so instead of what we're used to, like for example, say a nitrogen has 5 valence electrons, when we start connecting them, okay, I do away with the dots and now I'm connecting bonds. So each 2 electrons represents a bond. Okay, the reason I spread it out like this is because the valence shell electron pair repulsion theory. What that states is when you have electrons, these bonds represents electrons. Opposites attract, but like objects repel. That's where the repulsion. So if I have 2 negatives coming together, they're going to be repelling each other as far apart from each other as they can. Like objects are going to repel. That means they push apart. So these electrons have to be drawn as far apart from one another as they can. So that's where the VSEPR comes in. Valence shell electron pair repulsion. You're going to push them apart as far from each other as you can. Okay, so we don't do drawings like this. That has nothing to do, we're observing VSEPR. Okay, so we draw them as far apart from each other as we can, because like objects repel. It's not like positive, negative, we're going to talk about later, like magnets, they attract. Opposites attract, like objects repel. So we're going to push them apart as far apart as we can. So step number 2 is our drawing. Okay, so now we're at step number 2. Okay, so now our job when we draw is to make sure we have 8 valence electrons, also observing our octet rule. Now, it has up here the exception. The 3 exceptions are going to be obviously hydrogen and helium, but the other 3 exceptions, other 2, will also be beryllium and boron. They cannot fit the perfect octet rule when we draw them. When we draw them now, not for just valence electrons. So now we're going to start drawing. I have hydrogen. Hydrogen can only have 2. That's one of the exceptions. Okay, because I'm filling up my first orbital. Remember, the first shell is actually full when it has 2. So hydrogen is one of the exceptions. It only has 2. So my job is to make sure all the other elements beside hydrogen, boron, and beryllium have a perfect shell of 8. All right, so let's start counting. 1, 2, 3, 4, 5, 6. Well, nitrogen is supposed to have 8. So I need to draw 2 dots. So now it can have 8. So 1, 2, 3, 4, 5, 6, 7, 8. The whole goal of when you're drawing, make sure each separate individual element is surrounded by 8 electrons. Okay, now it also has to meet the valence rule. My 8 valence has to be connected in my big drawing. So let's see if I have 8, if it matches. 1, 2, 3, 4, 5, 6, 7, 8. And make sure each one has met their perfect octet except for hydrogen. Hydrogen only has 2. Okay, so I've met my perfect 8 and perfect 2. And I've also met my valence numbers of electrons. Okay, if that fits, then we go with that. If not, then these other steps are going to have to come into play. If we do it and it didn't match, like the next problem we're going to work, it's not going to match. So we're going to have to do a double bond. If double bond doesn't work, then we have to go back and do a triple bond. Okay? So the whole goal is to make sure each element separately follows the octet rule And then they also match the valence numbers of electrons that you've calculated. Alright, so after we do step number 2, which is the drawing, then step number 3, I need you to look at your next important sheet, this one. Now it's time for us to figure out, after we draw it, what is the molecular geometry. So step number 3, determine the molecular geometry. Now, on the test, I was telling first period, I will let you use this sheet, but for the 6 weeks big benchmark test, I expect you to know this. For the benchmark test this time, it's going to be more difficult because you're actually going to be drawing, proving that that is your answer. Still going to be study island, but you're going to be writing this stuff out. Okay? No more A, B, C, D. You're going to prove to me, justify your answer. All right, so next step, determine the molecular geometry. So how do we do that? Let me show you. So look at your sheet. It says number of atoms on the Ca. Well, Ca stands for central atom. I need you to write that down. Number of atoms on the central atom. Number of lone pairs on the central atom. Then it has bond angle and molecular geometry. Then it gives you some examples. All right, so let's look and see which one matches up with what we have. All right, class, how many atoms do I have attached to my central atom? 3. How many lone pairs do I have? This is considered a lone pair. 1. So I need to look for 3 and 1. Which molecular geometry matches up with 3 and 1? Trigonal pyramidal. So step number 3, my answer for step number 3 is trigonal pyramidal. Because I have 3 atoms attached to my central element. Okay, so like I said, you're allowed to use only this sheet now. Well, of course you can use your reference table. Just this one sheet out of the 5. All the rest I expect you to know. And the more you practice it, the better you're going to be. So like the first 2 will be long because, well, the first one obviously will be long because I'm showing you how to do it. The more you do it, the more you practice, you should be able to do these problems like that. All right, so what's step number 4? Let's go down. Step number 4 is going to involve our next sheet, which is, I need to look at your homework sheet. Your homework sheet said indicate whether the molecule is polar. All right, so here's where your little PowerPoint comes in. So step number 4, determine the polarity of the molecule. Polarity of the molecule, not if the bond is polar. There's a difference between talking about the polarity of the molecule and whether a bond is polar. So I can have a polar bond, but have a non-polar molecule. So what does polarity mean? Polarity is based on the symmetry. So this is where this PowerPoint, so instead of teaching students symmetry, because I always get these funny faces, people forget about what symmetry is, where you draw a line straight through your structure. You did that in math, but that seems to confuse people. It just goes over their head. So I want you to learn the easy shortcut method. So look on the last page of that PowerPoint, which says easy shortcut. Now you can read through the rest. It talks about what is symmetrical and what is asymmetrical. That's basically what polarity states. If a molecule is symmetrical, a mirror image of each other, but I'm going to teach you the easy shortcut way. There are 2 ways to determine the polarity of a molecule. Condition number 1, if you have a lone pair. Condition number 1, lone pair on the central atom. Well, that's easy to identify. Lone pair on central atom. Second way, if I have different elements attached to my central atom. What do I mean by that? So let's look at an example. Different elements other than one attached to the central atom. I'm just going to abbreviate from noun and put CA. Okay, so what do I mean by that? Look on the other worksheet I gave you that has H2CS example. H2CS. Okay, if I'm looking at H2CS class, which one of these three elements would be my central atom?
C.
Right, C. But why didn't you choose H? Right, hydrogen can never be the central atom. Okay?
Why wouldn't it be sodium? Or not sodium, sulfur?
The least electronegative.
Closer to the left.
It's closer to the left, remember?
That makes sense.
Right. Your central atom is always the element that is your least electronegative. We've already learned about trends. So the trend is, as you go from left to right, they become more electronegative. Carbon is to the left of sulfur. So carbon's my central atom. So this is what I would do here. Okay, so I have different elements. Unlike what I'm doing while in this particular example, NH3, I only have one element attached to the central atom. Here I have sulfur and hydrogen. So in that particular example, this would also be polar. So you have two ways to be polar, a polar molecule. Number one, if you do have a lone pair attached to the central atom, or if you have different elements attached to the central element. So let's go back to our problem we're currently working, which is NH3, and you tell me, is this a polar molecule or a non-polar molecule, based on what you see? It is polar. How do you know? It has a lone pair attached to the central atom. If you have a lone pair, or if you have different elements attached to the central atom, then your molecule will be polar. If you do not have a lone pair, they're just all straight bonds, or if you do not have different atoms attached to the central element, then it will be non-polar. Okay, so that's how you determine the polarity of the molecule. All right, we got one more step to do. That's the one I wanted you to add on your homework. Your homework just tells you to stop right there, but I wanted you to take it one step further like they did in the last questions, 1 through 10. Put comma, state the intermolecular force. So step number 5 is to state, and we're going to talk about what IMF means. State the intermolecular force. All right, so that's where this sheet comes into play. I'm getting ready to teach you the 3 types of IMFs, and I'll just abbreviate from now. You know, IMF means intermolecular force. The force is within that hold those molecules together. So we have 3 intermolecular forces. I'm going to teach you in order of weakest to strongest. The first intermolecular force is called London dispersion. So let's talk about that. Number 1, London dispersion. These are the forces inter that holds them within. London dispersion forces. Okay, what does that mean? First of all, the only way you can be London dispersion is if your molecule is non-polar. If your answer comes out to be polar, it cannot be London dispersion. Process of elimination. Okay? Non-polar molecule. So that's why these steps, you're going to draw me a flow map tomorrow. This is one of those, when you do steps, these steps have to be in order. There's no way you can determine the intermolecular force until you know step number 4, which is the polarity of the molecule. There's no way you can know the polarity of the molecule without knowing step number 3, which is the geometry. You can't do step number 3 until you do step number 2, which is the drawing. Well, you can't do step number 2, the drawing, until you know the valence numbers of electrons. So this is a chronological flowing. You can't do step 5, you don't know what you're doing. You have to do them in order. Step number 1, write the valence. Step number 2, do your drawing. Step number 3, determine the molecular geometry. That's this sheet. Step number 4, determine the polarity of the molecule. And step number 5, state which of the 3 intermolecular forces this involves. Alright, so the first one, London dispersion, it is the weakest of the 3. So let's talk about what it is. The weakest of the 3. Okay, so when you think of London dispersion, just think about like the paper does. It's not really like magnets, but you have like positives and negatives all over the place. You have a very weak force of attraction. So it is the weakest of the 3 intermolecular forces. It's a very weak force. Remember, and let's go back and attach that to that electronegativity trend activity worksheet you did. If your electronegativity was between 0 to 0.4, you chose nonpolar. Now you see why. It is the weakest of the 3 intermolecular forces. All right, next intermolecular force is called dipole-dipole. For dipole-dipole force, I want you to think of little magnets. So when you think of magnets, you think of forces of attraction. So dipole-dipole, think of little magnets, and I've drawn the picture down here. So these are like a stronger force of attraction. Why? Because the positives and negatives are closer to each other. So think of dipole-dipole as like little magnets. You have your positives and your negatives attracted to each other. So this would be a stronger attraction. Stronger, obviously, than London dispersion, which is just kind of all over the place. So when you think of dipole-dipole forces, think of, now the only way you can be a dipole-dipole, let me come up here, you have to be a polar molecule. So when you determine in step number 4 that the polarity of your molecule is polar, it's only one of 2 choices. Well, we've eliminated London dispersion. The only way London dispersion can happen is if it's nonpolar. So if you determine in step number 4 the polarity of your molecule is polar, you have one of 2 answers. It can either be dipole-dipole, or it can be hydrogen bonding, okay, which is the third one we're going to talk about. Okay, so number 3, your third intermolecular force is called hydrogen bonding. Flip over on the back. So what do I mean by hydrogen bonding? You have to have a hydrogen. It floors me every year when people choose CN and they tell me that's a hydrogen bond. If you do not have the element hydrogen in it, it cannot be it cannot be hydrogen. Okay. But you would think that would be common sense, but every year people tell me on the test, oh, this is a hydrogen bond. Really? Where do you see hydrogen? Okay, so some of these things are common sense, okay? The first stipulation, in order for it to be a hydrogen bond, you have to have hydrogen in it, okay? And then it has to be attached to a very extremely electronegative element. Attached to, I'm going to put a high electronegative element. So what do I mean by that? And it tells you specifically, to a high electronegative element. Meaning nitrogen, oxygen, and fluorine. Now carbon is iffy. Sometimes carbon is within a hydrogen bond and sometimes it isn't. But always, no exceptions. It will always be, if you have hydrogen attached to an electronegative element, meaning all the time, nitrogen, oxygen, and fluorine. Because you know the trend, as we go from left to right, that just makes sense. Electronegativity is increasing. So if you have a hydrogen and it's attached to a nitrogen, oxygen, and fluorine, it will always be a hydrogen bond. Carbon, sometimes it just depends on what else is paired with. Okay, so let's go back, and now you're gonna tell me the answer to number 5, the 5th part of your homework. So let's go back to our drawing.
So on a, like, test, we have to write all of this out right now,
Yes, but you're not gonna write the notes. A lot of this is long because I'm explaining. Now, we're gonna do the next one together, and you're not gonna include the notes, but it's still gonna be a whole page, or 3/4 of a page. All right, so tell me, class, where are we? Based on what we said, what was number 4? Oh, we said that this is a, did we write this? No, we
Yeah.
did not.
We wrote it up there by the drawing.
We did?
Yeah. It's
Okay, it really should be under step number 4, determine the polarity.
It was long
right
period.
now.
All right, so this is a polar molecule.
Wait,
So from now, like for homework tonight, when you get to number 4, just put polar. You don't have to write all this stuff. I'm just doing it because to show you how to do it. All right, so since it's a polar bond, polar molecule, we've established it's a polar molecule. What are my only 2 options?
And
Hydrogen or
that
dipole.
one.
So, our question was, our formula was NH3. So is this dipole, or is this a hydrogen bond?
Hydrogen.
This is a hydrogen bond. So from now on, when you're doing homework, you don't have to write all this stuff out again. You just write the answer, hydrogen bond. Okay, like I said, it looks like a lot because I've described a lot of explaining, but step number 1, let's go back. And then once you do it, like I said, it's gonna become quicker and much easier to do. Step number 1, write your valence. Step number 2, you're gonna draw it out. Step number 3, tell me which which molecular geometry it is based on your sheet. Step number 4, tell me the polarity of the molecule. And then step number 5, state the IMF. All right, so let's do one together. That's a little bit different. We haven't done before. Let's do number 7. The one that has an anion in it? No, because I'm in the middle of talking. No, sir. Once I finish and you start on these. So let's do number 7. 7 says Cn -1. All right, now I want to see tomorrow when you turn your homework in on my desk, I want to see 1, 2, 3, 4, 5. All 5 steps. What's my first step, class? What do I do first? Okay, so how do I do that?
You write out the element.
Right, first of all, I have to separate the elements. All right, so I'm going to write C, and I'm going to write N. Okay, what family is carbon in? 14. So how many valence?
4.
How many atoms of carbon do you see?
1.
Right, if there's no number, it's understood 1. All right, what family is nitrogen in?
15.
So how many valence?
5.
How many nitrogens do you see? 1. All right, and then we have to include, of course, our -1. What does -1 mean? Plus 1. So what's 4 plus 5 plus 1?
10.
All right, so I need to account for 10 valence electrons. So in my drawing, I have to have 10. Okay? All right, step number 2, I'm going to draw it. Which one between the 2 of these, carbon or nitrogen, is my central atom? Why? How do you know that? Farthest to the left, excellent. So I'm put carbon and then nitrogen. Well, I didn't have anything else bonded, so it looks like that. But carbon is my central atom. That's why I'm gonna put other electrons, it needs to go there. Alright, so the goal, when we draw, is to make sure each element, except for those three exceptions, hydrogen, boron, and beryllium, they have to have 8 electrons surrounded. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I've made sure that each element follows the perfect octet rule. Okay? This is why this is trial and error. You're going to have to use a pencil. Okay? Sometimes we're going to have to go back and erase like this one. Okay, so I met my perfect 8, but did I meet the 10? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's way too many. I can't have 14. The rule says I have to have 10. All right, so let's start. This is where the other steps on this sheet come into play. If it doesn't work with a single bond, then we go to double bonds. Okay? So we got to erase this. That's not right. We met the perfect octet rule, but we did not meet the number valence requirement. Okay? So we got 1, 2. Let's try a double bond. See if that works. 1, 2, 3, 4, 5, 6, 7, 8. Okay? 1, 2, 3, 4, 5, 6, 7, 8. All right, so both of them now meet the requirement for the perfect octet rule. So let's see if we meet the valence requirement. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh. Not right. Okay, let's erase again. So we tried single bond, it did not work. We tried double bond, it did not work. So let's try triple bond, okay?
This is a lot of bonds.
1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now this carbon has 8, and this nitrogen has 8. But now let's see if we meet our valence requirement. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, we do. So now we have determined this is a triple bond. Okay, so based on our drawing, step number 3 is what, class? What do I do next? After I draw it,
Determine the molecular geometry.
right, determine the molecular geometry. So let's go to our sheet. And how many elements do I have attached to the central atom? 1. Do I have lone pairs? Okay. So what would it be? Kind of tricky. What would you think it would have to be? Huh?
Bent.
Right, this has to be bent. So guess what? We're gonna have to go back and, you always start it drawing it a linear, but sometimes you're gonna have to make adjustments. So now we've determined it's bent. So now we're gonna have to bend it. So 1, 2, 3. Draw nitrogen. 1, 2. 1, 2, 3. Draw nitrogen and put 2. So sometimes you have to change your molecular geometry based on what your molecular geometry sheet tells you. Because we have, when we look on our sheet, it says number of atoms attached to the central atom. Well, we really only have 1, but we have 1 lone pair. Whenever we have a single element, we have 1 element attached to the central atom and we have a lone pair, that structure has to be bent. Even though they didn't put 1 up here on the sheet, think of 1 as your 2. The 2 and 1 matches up with bent. You always start drawing linear, and then you go from there. The rule is, I've got to tell you, always start drawing off linear, and then we can change the geometry as we go. All right, so we're going to have to bend that. All right, what's my step number 4? What do I do next?
Determine the polarity.
All right, so let's look at my structure. Is this a polar molecule or a non-polar molecule? What are the 2 rules for polarity?
No
That's
pair on
cool.
a central atom or different elements attached to central. So is it non-pole?
It's got one pair, so it'll be cold.
No, but it's not next to the central atom, so.
Okay, which one is my central atom?
See?
Okay, do I have a lone pair attached to my central atom?
No.
No,
We
we
did.
did.
No.
Yes, I do.
It's up there.
Oh, I did that three.
These are the bonds. These are the two dots. That's a lone pair.
Looking at the model you did.
The bottom.
Oh, you know what? I didn't do that right. Thank you. Sorry, I didn't put my other two dots. Sorry, I didn't put my other two dots at the top. All right, I do have a lone pair attached to the central atom. So what is it?
Polar.
It is polar.
Wait, so,
Dipole,
so do
dipole.
we not put any on nitrogen? And,
We have
Oh,
dipole.
Lord, I left it off.
okay.
You gotta show your 8. Yes. All right, so this is polar. How do you know again?
Because there's lone pair connected to the central.
Right. There is a lone pair attached to the central element. Anytime I have a lone pair, or if I have different elements attached to the central element. So we've determined it's polar, so what are my options for IMF?
Dipole, dipole, or hydrogen bond.
Yes, either dipole or hydrogen bond. So if this is my atom, CN, -1, what is my only option?
Dipole, dipole.
It has to be dipole. That is my only option. I see no hydrogen in that formula whatsoever. All right, so the second time, see, it wasn't as bad. See, I just attached notes. So you might could do a half a page, not sure, but I need that drawing to be big. You might could do it on a half a page. Put 2 on 1 page.
I got a part of it. This is like after. No. Cause I've already done number 2.
Oh, okay. All right, any questions on that? Perfect timing. Now, you and your partner can start working on, probably get one more done. I think we got about 5 minutes.